Yes, so it's recording now. Okay, good. So in very principally, how does the structure of these types of problems look like? Well, this is shown here. This is from a review of modern physics that came out a couple of 1 or 2 years ago. And basically, the way that people look at these kind of variational approaches is to divide the whole algorithm up into a quantum part and into a classical part. So we have here the kind of core quantum part where there is some kind of input into that state, which is just the computational input 0. So that shows that there is no need to have any kind of memories here. All that you do is you start with all the qubits in state 0. And then there is some kind of circuit, a parameterized circuit, that turns this input state into the state that you want to basically represent the optimal. And that actually gives a solution to your problem. Now, this parameterized circuit that you have here consists of kind of all sorts of gates that you might want to think of, but importantly, they are parameterized by classical parameters. And so the state that you produce here is a complex quantum state that comes out there, but it is characterized by these types of parameters that you have here. So that means that the information about which state you have generated is stored classically in a set of classical parameters that tell you how you take the initial state of your input qubits, how you rotate them around the Bloch sphere, how you operate on them. And you can thus reproduce this state at will by just storing these classical parameters. Till it turns out that even a kind of small number of such rotations provides you with states of complexity that you could not create otherwise. So it's very simple to see that if you wanted to characterize this state that comes out here, this is exponentially hard in the number of quantum gates that you have here in general. So we can generate very complex states very quickly with just the application of a couple of 2 and single qubit gates. And then basically here we expect that state, that parameterized state, to be what I would call the approximation to the solution that you are searching for. And what you then need to do is you need to measure this state to be able to work out what the kind of cost function is that you would want to optimize. And in order to do this, one usually wants to then rotate this state that comes out here into the basis that you can measure in, which is the computational basis. So after this kind of parameterized quantum circuit, there is another layer of quantum gates that just rotate all your qubits in such a way that you can then subsequently measure them in the computational basis. And these measurements then provide you with certain probabilities of each of these qubits to be either in the state 0 or 1. Okay. Now what you do is you take these output probabilities and feed them into cost function or into a kind of objective function over here, which basically means you have some objective function of these classical parameters here that parameterize your quantum circuits and the measurements that you have done here. So this is classical, these are the measurement results, these are the parameters that determine your circuit. And you then want to minimize this function to classical optimization. So what you do is, you here do nothing that is in any way quantum, but you just look at how does this function O change with these parameters theta, either because the parameters change directly or because they change and change this circuit here and hence change the probabilities of getting certain values out for the qubits.
Okay.
Yes.
If you optimize, there are two strategies. One is global, you want to label it like that, and the other one is local.
Yes.
Which uses gradients.
Right.
Now, if you search into a large parameter space, you probably look for global. Or do you combine with local, or
so
do you have a fixed in engineering? If you do design optimization, if Volkswagen, for instance, sells a car, the new car does not look radically different from the old one. So they start from an existing proven design, which has its benefits. which allows to use gradients because you have a very good base point from which you would like to explore your opportunities.
Yeah.
How do you do that here?
So here you can do something similar. So basically you can either do here global optimization without any gradients, and of course that is difficult and is
very important, costly.
It's costly, and you usually end up in some kind of local minima or what is called disparate plateaus that you have, and that is typically not really, you know, the kind of thing to do. But then of course you can do, as you say, you can also use gradient-based methods, and there basically you know how to change this network here to, instead of giving you the optimization function O, to give you the individual gradients. So you can basically use from a known network, you can work out what the gradients look like, and you can then use gradient-based optimization methods.
Requires a network which has some trust that network to
or either that, or you just use this network to encode the difference from the old scheme, I would say. So that's basically what you would do. You would say if the network does nothing, you basically get back the old scheme. You see here you can put any kind of known parameters or anything known you can put into the classical world, basically. You can just do the difference from the current design or different from the current solution. And then you can either here work out the kind of objective function O itself, or there are these kind of auto-diff networks that basically automatically work out gradients in different directions. And yeah, yes.
So just on that point, so isn't it that you're minimizing like the change in the function, like time?
True. In the end, that's
So
that's
would
really
that always be variation? Like that would always be like a small change to the function
in each step.
in each step.
Yes, but of course, if you start from something that is completely unknown, so yeah, then you need extremely many steps to get to your minimum, and that is typically undoable. So what you want to do is you want to start close to a solution that you know already, or some kind of design that you have already, and then just optimize by going along the gradient that minimizes.
So what is the cost function? Maybe you're going to talk about this later, but
so in our case, then there will be specific cost functions. I mean, I'm just here, this is just a generic setup that you have. I mean, this captures all, basically. Yes?
Maybe it also vanishes when we touch our cost function, but what is, if this optimization problem is now non-convex, is the gradient approach then not?
Then you have exactly the same problems as you have in classical optimization. So this type of optimization problem does not get rid of the kind of problems that you have in classical optimization. Okay, I think that one can say from the start. What actually the advantage is, or maybe, is that evaluating this cost function here can be exponentially faster, or it can be at least kind of much faster than on a classical computer. And so you basically still need all of your great optimizers. We have just asked them to install Gurobi here, which we've never used before, but apparently that's one of the best ones. And you still use your classical optimizers, but you apply them to this kind of cost function that you obtain from a quantum computer. Okay, and that has, that doesn't solve your classical optimization problems from the start, but it does have some nice properties to some extent that sometimes make your life a bit easier, because you know that your cost function comes out of the quantum measurement, so it comes out of this evolution that we have here, so it can have properties that make it somewhat nicer than if you knew absolutely nothing.
Dieter, may I?
Sure.
Just, I mean, maybe another way to see the value here, I'm not sure if you mentioned it, I had to pop out for a moment, is that the answers, the parameterized answers we build it based on the problem we have at hand. For example, in quantum chemistry, where most of these things started, which is a quantum problem, using a parameterized quantum circuit to generate a trial quantum state, by default brings you closer to that area in the solution space that you hope you have a quantum advantage, but also a kind of an easier job in the classical optimizer. So they are both kind of go hand in hand in this sense. The
Right.
quantum, yeah.
Absolutely, you're absolutely right. So that's no, I think we discussed this to some extent just before. That of course you want to start with something that is close to your solution already, and of course that would be one of the goals. And then optimization gets easier, but it does not solve you the problems of classical optimization. Just to be clear about that, this just doesn't do it. But then, of course, as Dimitris was also just saying, working out the cost function can be much more efficient than classical. Okay. All right. So basically, that is the kind of route that you go through in the most generic way. And of course, what we have as inputs here. These are these kind of theta zeros that would be precisely the guesses that, of course, the better the guesses, the better the overall thing. You need to give the thing the objective function, whereas the output, you should get the optimized function and the value of this kind of optimized objective function. Okay, so that's in principle how this works. That are the main part of this type of setup. Now, one of the questions that we've also been discussing, and that I just wanted to point out here, is that this structure here, because you have these values of theta in there, and you have here something that looks like a Hamiltonian, the question is this somehow a situation where you can only optimize over Hamiltonian systems? Because, of course, Hamiltonian systems are always nice. You basically don't need to deal with your differential equations. You just work out the Hamiltonian and then off you go, and it's easy. So that's maybe a bit deceptive, because what this Hamiltonian here can be anything. It doesn't have to be Hermitian. It doesn't have to be. It doesn't have to have any properties. And the reason why this is the case, I'm going to show now. I've included a number of slides here that basically summarize what I'm saying, and I've uploaded this to the Teams so you can all have a read through that, what I say. And the reason for this is maybe a bit technical, but essentially what happens is that if we take the space of the states of the qubit, then basically the basis in the operators on that space of the qubit can be the Pauli matrices. So if we take the identity matrix, the X, Y, and Z Pauli matrix, then these operators form a basis of all the operators that you can apply to a qubit. And of course, if you limit your prefactors here, the C0, C1, C2, C3, to real numbers, then you always get something which is unitary and Hermitian. But if you allow these numbers to simply be complex, then you can represent any H that you want here. So the technique that you would then use, and this is also why this kind of optimizer had this rotation into the right basis before, you split up your objective function into these kind of Pauli operators, X, Y, and Z. And you say you measure the C operator, you can always classically multiply this with a complex number. And you measure the X and the Y operators, and you can, if you have something that is non-Hermitian, you can just multiply classically with a complex number and get any operation, or minimize any operation, any matrix on a single qubit in this case. Okay? So because of that, this is not limited to Hermitian matrices, but of course, for the question then arises, how many such terms do you need if you have a larger system? And basically, if we now take n qubits, our Hilbert space is a tensor product of n such two-dimensional Hilbert spaces. And then what we need to do is we need to decompose the operator that we want to measure into products of Pauli operators. Okay, that's shown here. So basically, these products of Pauli operators can always provide you with a basis for any operator that you want to optimize. And so in principle, therefore, you can always optimize any operator that you want, any kind of function that you want, but you may have to decompose this function into a sum of terms that you can actually measure. Okay? And so one of the kind of challenges in all of these variational approaches is that you need to find a set of operators that you can physically do and that don't grow exponentially with the size of your problem. Okay, so in quantum chemistry applications that Dimitris was previously mentioning, you usually get that you need a number of Pauli strings that goes up with the number of orbitals that you want to have quadratically or cubically or something like that. So it can be that you need a lot of those Pauli strings. It can be several thousands, several millions, but it usually does never grow exponentially. And as long as it doesn't grow exponentially, if the system is large enough, you gain over what you would do classically, but of course, maybe only down in the future. Okay. And so that's just to kind of show that we are not limited to any kind of Hermitian or Hamiltonian system. The optimization that you want to do can be done for any objective function that you have in mind. Okay, so that is the generic setup. Just to mention that briefly, that people have come up with already back in 2014. And basically this review that I showed you that I've cited, that is a kind of 50 or 60 page paper where you find almost anything you want to know about this kind of standard optimization problems. Now, what we've been doing, and I skipped through some of this, what we've been doing is, so you can read on that, what we've been doing is we've basically developed ideas for how to specialize this type of ansatz and make it simpler and actually make it more transparent for these types of partial differential equations and particular fluid dynamics problems that we want to solve. And so what we've been looking at is precisely starting with this Navier-Stokes equation incompressible as shown here. But of course, we've not gone straight away to the kind of sophisticated approaches that Thomas has shown before. We stuck with the very simplest thing you can imagine. We just did a kind of simple Euler step in time and then evolve kind of without boundary conditions in 2 or 3 spatial dimensions. And what we do there is basically we say that if you take this set of equations, you can actually define a step in time delta t to go from a velocity field v to a velocity field v star by minimizing this type of cost function here. So if we say that v is our known velocity field at time t, and v star is the new velocity field at the later time, then basically if we find an expression, if we find a v star that minimizes this, then basically the new solution fulfills this equation again, but at a later time step delta t later. This first term, as you probably all see, is exactly this, this pressure conservation and using a penalty method, which I think I know is not very kind of useful for you guys, but for us, this is the simplest thing that we can do. And then we just do a simple step. Now, I should point out that this is, of course, what you do if you just try this out and try it for the first time. You do the simplest thing that comes to your mind, and you try to implement that and see whether this can work. The important thing is that here, what we see is that this expression that we need to optimize, this follows, of course, from what we've just heard before, from doing a time step and wanting to find the new value such that the kind of an overall equation is fulfilled. But this cost function that we have here contains only terms that have this generic form here. So we have some functions, fj, so that could be the flow fields, different components in x, y, and z direction. That could be pressure terms. That could be all sorts of other kind of fields that we want to optimize over. Then products of those, and each of those can have some kind of linear differential operator applied to it. And so if we look at all of the terms, and unfortunately I have not seen other terms today apart from this kind of strange maximum function that you guys use all the time for the upwind, I've not seen anything that doesn't look like that. Okay, so in particular, there are no terms in there where you need any kind of exponential of the velocity field or some kind of sine function of the velocity field or anything like this. All that you have is always powers of the fields that you want to optimize over. And some operators like these kind of Laplace or Nabla operators, and then you multiply these things together, you integrate over it, and that's what you want to optimize. Now, I hope that that is true, because if one ever need something that looks very different from that, we'd have to think again. But so far, all that I've looked at, I never saw anything else. Is anybody? Yeah.
Sorry, Peter.
Yes.
Are you fine if we ask questions?
Sure, please go ahead. Yes. Yeah.
Okay, sorry, because I'm not sure whether you see us at all, but okay, so could you, because this is crucial for me to understand, to be able to follow. So could you explain this again, how you map now, how you go from the partial differential equation that you consider to now the cost function?
This cost function. So
Yeah.
basically, what you write down is you write down just a time step. So basically, you say you have here this dv over dt is nothing but a v star minus v over delta t.
Mm-hmm.
Then basically from that you get an equation for the v star that should be equal to 0. And then you basically here say that you have got the pressure term, the kind of or the divergence of the velocity field, that must be 0. So what you do is you basically take all of these terms that must be 0 and put them into a cost function that you basically take the modulus and square it. And then you say, if we find the minimum of that expression, we have a solution.
Mm-hmm.
So
And then to go to the, exactly, and then to go to C?
To go to C. So to go to C, I do really nothing. All that I say is, if I look at the upper terms here, so for instance, take that first term here, that first term is a V star, and then take in the divergence of the first term. And the divergence of the first term is the same as applying a linear differential operator to some kind of function fj, where fj in this case would be V star. Or the second term is, just basically take here the Laplace operator applied to V. So OJ here would be the Laplace operator applied to V, work out the modulus squared. Because all of these terms are always of that type of form, at least, yeah. And so I can just generically write it like this. Any function that appears in here is of this form. You have another question, yes?
Is there any reason you took the norm 2?
Well, we took the norm 2 because the norm 2 is what we get straightforwardly in quantum physics.
Okay.
Norm 1 is much harder, or nearly impossible. Yes.
What did you do with the pressure?
So that's here. Oh, so because if we enforce this, then the pressure disappears.
Because that's not what we tell you true. So I think in your computation, you wrote that as a Lagrange multiplier from that.
Yeah, so I'm not sure. I mean, if we can ensure that this holds, then this must be gone. Or
In
not?
some flows.
In some flows. In the flows that we can see. So this is not, I mean, under what condition would this not hold?
Imagine you have a duct. Pressure at the inlet is in each plane of the duct, the pressure is virtually the same.
Yes.
But as you go from inlet to outlet, the pressure drops linearly. So you would have a gradient.
You would have a gradient.
Otherwise, the flow would have no reason to go from inlet to outlet, either driving pressure gradient.
So in the
The
examples,
velocity is divergence. You see a pressure gradient contribution.
right. So in the examples that we've studied so far, this never happened. There was no inlet or outlet one. No, there's no pressure change.
Well, there are examples which work basically without the pressure gradient, but the flow is gradient driven, which is for internal flows.
Yes.
Duct flow is always.
So
But you would have a solution for that. You just include the gradient of the pressure
exactly.
to your
Yes.
second part of the objective function now,
Exactly.
and determine it from the result of the first somehow.
Yeah, that's what we would do. I mean, that's what we did for the second example, where we actually had this kind of lit-driven cavity. We had to keep that term. But for this, what I'm going to talk about now, we didn't need it. Just dumped it completely.
Yeah, one small question, the maximum R here for use is 2, or
Which R?
in the right upper.
R. No, R can be anything. The R can be anything, but the bigger you make R, the more quantum registers you need.
Okay, so this here.
Okay, so that basically just tells you how big your quantum register is. But essentially, what this means here is you have F1, F2, F3, F4, F5, F6, and so on. And each of these Fs is one of the kind of quantities you have as dependent variables. Okay, so as I said, velocity fields, temperatures, pressures, or whatever, and you can multiply them together. And you can't take the power. You can't take the velocity to the power of the pressure. But I guess that's not something you hopefully do.
What is,
So what is?
you can't put the function into the power, or
You can't put the function into the power easily. Yeah. So you can do polynomials of the function by just choosing. If I choose a couple of those functions the same, I get the function to the third, to the fourth, to the fifth power, and so on. But I cannot take the function easily into the power. That would be hard. But I've not seen that, fortunately, in any of the examples.
So for this example, so if we now, do we now simulate each term separately, or do we just?
Too easy. Yes.
So for the second term, we now would need, for the time derivative, there's power of 1, then we have power of 2, then we have power of 1. So if we would have in one circuit, then it would be, I think, R equals 5 or 4 or something. Yeah.
Right, exactly. So you would have a couple of terms that you need, but of course the number of terms that you need will always kind of be the number of terms that you get in your equations themselves. And so that would be a kind of small number in general.
And they are all having the same term you just said. So our cost function drives our control, which is in the answers. They are now just all copies of each other.
Yeah.
So we would have just one set, which we just duplicate.
Yes.
Yeah.
So basically what you need is, for each of these cost functions, you need a couple of qubits to represent them. So say for each of these functions that you have in there, you need 20 or 30 qubits to represent them. And of course, if you have 5 terms, then you need 20 times 5, so that's 100 qubits. So that's why we come to the conclusion that a quantum computer with a couple of 100 qubits, say 200 qubits or so, could solve these problems with kind of very good accuracy if it is sufficiently error-free. Okay, that's a big if, but that's not my job. The error-freeness of the computer, that's for the hardware developers to do. And of course, they have promised us enough that we can go and do it.
is you solve an optimization problem.
Yes.
And you have these two forms which you add to the total. There's a weighting function in between these two forms.
Yes.
Is this a static value? This
for us, it was, but you can of course change it. I mean, you can basically in each step you could change that
using Lagrange principle.
Right. Yeah. Yes.
Because we typically experience that while we might initially converge very good on the Stokes part, at some stage the Stokes part doesn't improve.
Right.
Because everything is more the other way around. You don't see the second part at all for some reason.
Yeah, so that's somehow what we also saw in the literature cavity, that we needed to basically we needed to look harder at the pressure term there. But essentially, and that's the thing important to point out here. Essentially, what you actually put in here as these mu or these other parameters, this is something you can decide on your classical optimizer. You get these different bits of your cost function. You can choose these weights, all doing classical physics. And the other thing that I'm going to show is that working out this norm here is something that the quantum computer does automatically for you. So you don't have to integrate by hand, or you just measure. I mean, you measure the whole integral. So you basically measure this kind of two norm in just one go. Yes.
So I have a question about the construction of the cost function. So how do we project in the front side? Why do we project with the S1? Like I know that you don't have say, but like how do I know that you need to use F1 to project it?
Okay, so why we do that is because for this particular problem, this is just what you always need or what you always get. But it's kind of very simple to design a network that doesn't do this. and you could do something which has this F1 inside and just appear once if you wanted to. You could get rid of it completely. It just turns out to be the case that for these types of optimizations here, this is a kind of useful form to write it. And it also makes analysis of some of the terms that I want to show you easier, a little bit easier. But in the end, simple changes to the network will allow you to basically all produce functions that are of this kind of form. You can have this first term or not. And you just view it like this. Choose the first term to just be identity. And that's just the one. And then it works. Okay. Now, sure. Oh, yeah, Dimitris.
I'm just trying to see the equivalence of the Navier-Stokes to the non-linear string equation, your first paper in this series, right?
Yes.
That we have been. So in that case, you have the Laplace term, right? As you have it here, you have the non-linear term. You don't have the diffusion term, I guess.
Yeah.
And your cost function in that case was the energy. You have two cost functions, right? The energy and the distance between the vectors, the norm, right? The square norm.
Yeah. So
how does cost functions correlate to this red cost function? My question basically,
they are exactly of the same form. So the cost function there is basically is exactly of this form where F1 would be your wave function, your macroscopic wave function, and you need another F1, F2 equivalent to F1 to generate the nonlinear term.
Okay.
And because in the nonlinear term you have an F to the power of 4, so you need two more terms that are the same F.
Right.
Okay?
So long as in the NLSC, in the nonlinear string equation is F, the nonlinear thing is psi squared in the equation,
Yes.
right?
Yeah.
Okay.
And in the equation is psi. So okay, but let me say a couple of words to that. So in the first paper that we did on this, we did use the nonlinear Schrödinger equation, and of course the nonlinear Schrödinger equation is an Euler-Lagrange equation of a Lagrangian system with a nice Hamiltonian. Okay, and there, of course, it is much simpler to just take the Hamiltonian and minimize that. And so the cost function there was simply chosen from the Hamiltonian, from the original Hamiltonian, which, it would be stupid not to if you have a Hamiltonian. But since that question has come up, of course, I think it's important to see that this is something which can be done, even if you don't know the Lagrangian or don't know the Hamiltonian. But of course, if you have it, then why not use it? So if there is a simple Lagrangian, then you would always kind of start from the Lagrangian, minimize that. And there is now a paper, of course, where you can then also use the action principle, where you say that in what from the Lagrangian you minimize is the action over time, and that has the added advantage that you can then basically take time as another variable in your system to minimize over, and you then don't do time steps anymore, but you basically would minimize the whole four-dimensional function in time and space in one go. Okay? But that's something you can only do if you can apply the action principle, and I'm not sure, is this possible here for this? See, I tried to find out, I couldn't find it. I don't think there is really an action for the Euler for the Navier-Stokes equation. If there were, then of course this would be one way to do it. Does anybody know if there is one?
Good
At least,
question.
yeah, because if there were one, then of course you have other ways of solving it. But I guess if there were one, somebody would have found it. I guess we could. Okay, but this is just to illustrate that we don't need that we can just take the individual time steps that we do and write them as an optimization problem. Okay? And the optimization problem must be of functions of this kind of type, where you have powers of the function you want to optimize times some linear differential operators. Yes.
Can we additionally minimize
Yeah, yes, you can. So this would be what if you adopted the machine learning language, this would be what's called a hyperparameter. So it's not something that you directly optimize as part of your optimization steps, but it's an additional parameter that you put in, and you can choose and you run the thing with different values for that or with different behaviors of that additional parameter. But it's not a parameter that goes directly into your network that determines your variational function. Okay, and typically those things are called hyperparameters. But you could do it. Okay, so here is the network that we then have, and this is of course now simpler than what I showed you before, but reminiscent of what we had before. And so that particular is one big difference. So first of all, this part here is the same as what we had before. So before we had this big network that would create the variational state. So this was this variational parameters that determine this kind of functions. What I've done here is I've now divided this up into different quantum registers that contain these different functions here, F1 to F4. And so this should just indicate that what we want to have is different fields that we want to optimize. So F1, F2, F3 could be the three components of a flow field, and F4 could be the pressure field. And if we need higher powers of that, we just have more of those terms in there to generate these higher order terms for optimization. Okay, so basically, this is what we use to create the variational states. And this thing here, this network, that then works out the cost function or the part of the cost function that we want to optimize. Okay, so here basically these operators OJ are realized that basically take these various different functions and multiply them together with these differential operators contained. And now, because we just want the one cost function out, so one real value, we can just get this value out by attaching this whole thing to an ancilla qubit, and the value that we measure in the ancilla qubit will turn out to be exactly the value of the cost function. So that's the thing we try to minimize, and we don't need to measure all of these individual qubits here. Of course, we could do that, and this is, in principle, this is also important, that one has the ability to do that. But for working out the cost function, all you need to do is measure this network up there. Now, why would it be important to be able to measure these things here? Well, you would say if you have your setup and all you get out is the cost function, then what's the point of knowing the solution if you only can get out the cost function? Because what you actually want is you want some other things as well. You want your physically interesting properties. And now I would actually, I think, say something that you disagree with, I guess. I would say that one thing you don't want is the whole flow field. And if you ever want that, then of course, the whole thing is doomed from the start, because the idea is that you can make this computation on an exponentially fine grid, and hence reading out exponentially many points to know the flow field is defeating the whole purpose of this, to have exponentially smaller runtimes if you hope for that. But why would you need an exponentially many flow points? I mean, usually I would argue whenever you do a computation, you want to get out the relevant numbers and not as many numbers as possible. So what you could ask for is, say, you could ask for a coarse-grained representation of your flow field, or you could want to zoom into a certain point and read out certain regions of the flow field, or you would want to work out what is the, therefore what is the lift and what is the drag, and it's kind of global properties like that. And that's something you can do by operating on these qubits here. So in particular, if you start to basically put single qubit rotations on those, you can actually get rid of all the fine details in the in your flow field. And what you can then measure, what remains, is a coarse-grained representation of the flow field. Or in other ways, if you measure the kind of lower qubits or some of the lower qubits here, then what you can get is you can zoom into a certain region and find out what happens in that particular region, and you can then zoom in and see what the flow field looks like there. But you would never want to read out exponentially many points for you. Yes?
So if you just said that basically you have many details now representative in your quantum state, what you get in the end. So this means that each of these Fs is representing a different, let's say, dynamic of the problem.
No, they would all be the same dynamic of the problem, but in a lot of detail. So with an exponentially fine coordinate.
So this is not as we have in the Hamiltonian. So if the QMPU would represent the Hamiltonian, we would minimize. That would be like a variational quantum solver eigensolver idea. You get the minimal eigenvalue and the corresponding eigenfunction to that eigenvalue.
Yeah, no, so this is not what happens here. So what you need to do is you need to basically measure this ancilla qubit until you have a good measurement of the average value. And that means you need to measure as many times as you require to make the variance small. And then basically fluctuations around that mean that would correspond to different realizations, but not physical realizations of your actual fluid dynamical system, but of your quantum system, which I think has nothing to do. So what you want is as the output, you want these parameters to determine these functions, and you want the kind of average value of this ancilla qubit measurement. You don't want any fluctuations around it, or so you want to measure as many times as you have to in order to get rid of these. So this means you still have to run this a couple of times to get the variance small. But, it should run, as long as it only needs to run polynomially many times, which we've shown is good enough, you will always beat in the kind of large limit, you will always beat classical.
Dieter?
Yes?
Looking at this diagram now once more, it reminds me some early works by Arthur and Carolina, like 10 years ago or so, 15 years ago, where, you know what I mean, this interferometric approach is you, instead of the QNPU, if you put a swap, and let's say you put a few copies of a, then measuring the ancilla, the visibility in the fringes gives you the trace, actually the overlap of your states. You can get the rho square, or you can actually see how far certain states are. Are you doing this now to estimate the quadratics, the kinetic, and so on, and on top you put this variational angle that you optimize on top? Is this what
that's exactly how you can see it. I mean, yes, I mean, that's absolutely right. And we cited the papers that you talk about in the original paper. And of course, you may remember I inherited Carolina from Alta as a PhD student. And so she worked on exactly those questions. And so that is in a way, similar to what they did back then.
Now the whole thing is very clear. That's good. That's good. Yeah. It's good that we go back 20 years ago. So.
Yes, you can. So basically, if you do the simple swap, then this is basically you measure the traces. Exactly. That's precisely that. Yeah.
So now you just need to modify your QMPU to generate all the terms whenever you have an LSC, stocks. So okay. Yeah, and on top you put the angle there that was not there 10 years ago. There was no variational approach on top. Okay.
Exactly. Okay. Yeah. But otherwise, this is similar. Okay, so just to kind of show you again, yes, you have a question.
I just wanted to ask about the Fs on the previous slide. So in some cases, those Fs are obviously the same.
Yes.
So I guess that means that the variational angles that you need to generate that sort of be the same. Yeah. And you have to have like a correspondence between the different qubits.
Right. You need to be able to create the same network or multiple copies of one of the same network. Absolutely. Okay, so here again, this is nothing different. Oh, yeah, yes.
I have a question, maybe we'll come to that later. Of the trade-off, you get like this speed up due to the exponential reduction of the dimension.
Yes.
But at the same time, you cost everything in an optimization process, which is, as far as I understood, usually not the way to do it. And I wonder how the payoff is. Yeah,
that's of course a good question. And this is precisely the question about what is the difference between, and I don't know that yet, what is the kind of speed difference between an iterative solver and an optimizer? And of course, you know, can you use the iterative solvers for that if they turn out to be faster? Because, you know, in essence, what you do is you evaluate what was the left-hand side. And then it's the question, how do you solve that? Do you solve that by what optimizer do you solve it? And I would argue that you could, you know, find ways of using these iterative solvers that exist. Maybe they're faster. So this is precisely, you know, this is precisely one of the kind of questions that we need to answer, is the question about what is the kind of classical optimization strategy? What is it that you want to do to basically do these time steps optimally? And, you know, what can you learn from the existing methods? Because, you know, as you're saying, it's not going to solve you those problems. What it is actually doing is it works out this kind of product of matrices and vectors and so on in one go without any overhead. And then, of course, what do you do with those numbers? That's the question. Okay, so here, these networks are precisely the ones that we had before. That now just we have a couple of copies of them that give us these different functions f. So I think there's not a lot to say, except, of course, I will say later that what you want here is you want a circuit that is finite. You want to actually be sure that you don't need too many layers of gates in order to generate a good ansatz for your variational trial function. So you must be able to represent your solution approximately with just a couple of gates. And that is one of the things that we've looked at already, where we actually can show that this circuit depth that is needed here is much, much smaller than the maximum depth you might need. And in particular, that generating this output states on a quantum computer is favorable, compares favorably to any classical method that would try to do this. So basically, the generation of these networks is something that is important to understand. And in order to understand this, so here's now a bit of kind of notation that I want to introduce just for those who may not have seen it. What we now need is we need to take these quantum registers and basically write down these product states of various different computational basis states. So for 2 qubits, we'd have these 4 states. We typically leave out this tensor product sign and just write this as a 0, 0. And if we have n qubits, we just write a string of zeros and ones, so just some binary string. And what I will do is I will rewrite this binary string as a decimal number with an arrow on top. So the arrow just simply means take the binary string of that number, okay, as a qubit state. And of course, this notation is not unique because you need to know how many qubits you have to turn this into the right state. But I just assume you know the number of qubits in the register. So you just fill up with zeros anything to the left of the most significant bit in your number, and then you should get the state. And now, of course, if we want to store functions in such states, what we see immediately is that the superposition of all of these different computational basis states, and there are 2 to the n of them, so if you have n qubits, there are 2 to the n of them, allows us to store 2 to the n probability amplitudes in that state. And those probability amplitudes are precisely the function values of our trial function that we want to have, okay? And hence, we can use n qubits to store 2 to the n function values, 2 to the n real values, and that is in principle an exponential advantage over what you could do classically. If I take here 100 qubits, I can store I can store 2 to the 100 function values, and that is beyond what you can usually do on a classical computer. And of course, that means that you have also far less memory to deal with. So all of these kind of memory constraints are a bit easier to handle. Okay, but now another concept that I would like to explain in this particular tutorial here, I wouldn't usually, is that we can take these types of states now and do what is called a Schmidt decomposition. And the Schmidt decomposition just takes this quantum register and splits it into 2 parts. And where you split it, you can split it anywhere, but you basically take the n qubits, like little n qubits to one side, capital N minus little n qubits to the other side, and you ask the question, how can I now rewrite that state in terms of those 2 sub-registers? Okay, and this is what I do here. So basically I have 2 to the n states in the original state, and then I split this up into 2 parts. where the first part here has m and the other part has m dash entries. So m dash plus m needs to be equal to this n. And we look at what happens if we rewrite the state in this way with the prefactors now, instead of having just a vector ci being turned into a matrix Cij. And you can now ask the question, how do you actually analyze, or what properties does this matrix Cij have if I basically, the row index enumerates the first quantum register and j enumerates the second quantum register, and we take that matrix and we can take that matrix and always decompose this matrix into a singular value decomposition as some unitary u times some diagonal matrix times some unitary v dash. And then basically we can rewrite that state as sum over only diagonal terms, dii times some phi I, where the phi I arises from this unitary matrix here and the basis states I that we have up there, and this curly phi I that arises from the second register and this unitary j. And rewrite it like that. And now, of course, the terms on the diagonal of this matrix, we can order them in size. So the first entry will be the largest, and then we get smaller and smaller and smaller values. And what turns out to be the case is that if these numbers in the diagonal drop off very quickly, then basically we have very little entanglement between the two quantum registers. If these values, if there are lots of them that are equally or nearly equally important, we have lots of correlations between them. And in the extreme case where all of these values are the same, we'd have a type of maximally entangled state between the two. So this also means that if this number here is reasonably small and we don't get too much entanglement between different parts of our network, then basically we know that we can generate this state efficiently in a variational network. Okay? And that's what we have analyzed for typical solutions of flow fields. How big is the number of terms that we need to keep in that expansion? When can we stop and truncate this sum? And if that sum can be truncated early, then of course we know that we can generate this state quickly with a variational quantum method.
Does it actually give you a prescriptive circuit for how to do that?
What do you mean to do the truncation?
No, like if you have these DI terms, can you then from that directly build a quantum circuit to this?
Yeah, you probably can, but we never did this. But I guess you could do that.
It would be actually, this is like a principal component.
Yes. Yes.
So people in old-fashioned mechanics, they call this reduced order modeling.
All right. Yeah.
And one could be tempted to run a reduced order model even classically, say, on the coarse grain mesh.
Yeah.
To generate trial functions. Basically, the only thing I don't know is how to refine them more. Size them or improve them.
Yeah.
Because of course a coarse grain representation can miss the flow topology. Might have vortices that you don't see on a coarse mesh. So your functions might also be not accurate enough, at least not to the level that we are aiming at.
Exactly.
But the question is it maybe it's possible to then refine and revise?
Absolutely. I mean, this is also what we wrote in that paper. I don't know who, it was either you or Payman who actually brought up this.
Input from there, yeah. I believe, to bridge technology.
Absolutely, I absolutely agree. So this is precisely what people would call reduced order models. However, the difference is that, of course, you here not need to put in what the coarseness is and where to stop, but we let the algorithm decide that. And so in a sense, the algorithm will actually pick what is the best basis, local basis, or the best coarse grain basis, the best fine basis, and where to truncate. And that, of course, means that we don't have to put the brain power in to do this, we let the algorithm do it. So in a sense, this is probably the main difference.
But wouldn't it be exactly the case? So if we have fine grids. And for the fine grid, we get now that, like, yeah, the last three modes or in that reduced order model, they are not really important for us. Then we have a set of small important modes or important states. Isn't that exactly representative to the coarser grid, where with the coarser grid, we would need to span up this kind of solution space in order to get these important modes covered? And isn't there a way that we could use the variational quantum algorithm only the coarse mesh then? Because as I see the DI, maybe it's not changing for the dynamical problem. So if we have channel flows, maybe when the first DI entries are the important ones, we could use the DI coarse grid and we could always extend to the fine world.
Exactly. So that's, of course, one of these ideas that came up also when we were discussing this early on, whether you would actually be able to use this kind of coarse and fine grid structure, or in this case, of course, we don't have I'll show in a minute, we don't have a fixed boundary, but we let that boundary roll to basically at some point say, here we cut off the variational approach, and we then close the physics to the very small scales using a different approach. And in particular, I think this is something that Payman Givy brought up, where he said, I want to study reaction flows with that. And reactions happen, he's doing kind of rocket science, these reactions happen at very small scales. And so I want to use the kind of reaction diffusion equation there at some point. I want to couple this to this kind of spectra of the DIs. And that's a question, I think that's a very interesting question that they are looking at for their particular flows. And I think that has some, I think, good prospects of happening. I can tell you in the quantum world, it's very simple, because there you can easily show that just simply cutting the spectrum off and removing anything below a certain threshold is optimal. So you can't do better than that. So there is no reason to kind of close off with anything else, because anything you do would be worse than just simply cutting off. Here we don't know that. So here it may be that kind of not just simply cutting off, but having some source term maybe that feeds into or takes energy out might be the better option. But I don't know that yet. So this is certainly something that we're going to look at. I think that would be very interesting. Okay, now, as I just said, we can do this decomposition with any cutoff of our quantum register into two parts. So there is no fixed no fixed size that we need to make that cut. We can do it anywhere we like. And so what we then do is typically we start off by just chopping one qubit off and leaving the rest, then look at the rest, chop the next qubit off, and so on. So we go step by step through the grid and look at every time just chopping off one qubit and then look at what remains in terms of this sum. So in that particular case, what will happen is this first term is just one single qubit, and the last term here contains all the rest of the quantum register. And then we look at what was all the rest before, chop off again one qubit, and then do this again. And each time we get this kind of diagonal matrix here. So for each kind of cut in the quantum register, we get a certain set of these kind of so-called Schmidt numbers, and we find out how much correlations we have between each of these different qubits and the rest. And now, if I take the view that I want this CII here to correspond to a function in coordinate space, the question would be, what does that mean in terms of that function that I decompose and that I store in this quantum register? And so I'm going to explain how we can intuitively view this in terms of the function that we want to represent. And so for that, I take a two-dimensional grid, and I pick out now not the first qubit only, but I pick out two qubits, because two qubits allow me to define 4 points in the grid, and hence they allow me to define the coarsest grid that I can think of. So imagine now your whole quantum register with this probability amplitude Ci, a chop of the first two. And the first two are the two most significant bits, so I can make them correspond to the 4 coarsest grid points that I can imagine on that fine grid. Okay, so I look at these 4 points, and I chop off those 4 points in the Schmidt composition as shown here. So my original flow field U of RQ is given here. That's defined everywhere on this fine grid. And then I decompose this just like I seen before through this singular value decomposition. Here, these lambda alphas are the DIIs that I had before. Then we have this kind of coarse-grained function. So this is now the 2 qubits chopped off. That would be the function values at those 4 points here. And this F alpha of XL contains all the rest of it. Okay, now you can ask the question, how many of these functions can I have? Now, if you decompose this, you can see quite easily that if I take 4 of these functions, so index alpha that is 4, namely 1 value for each of these points, I can reproduce any function that I like. Okay, that's pretty obvious because I have 4 points here, so I can choose these 4 function values to reproduce any function that I like. So the maximum number of terms I can have is 4. If that means I can have 4 such functions, and then of course 4 such functions are F alpha. And now that means that in this first step, the maximum number of terms that I can have in what was in this previous slide here, this kites, can be equal to 4. Okay, and now I have one function R alpha that describes my function that I want to realize on a very coarse grid. And the rest of it is all that is finite. So basically, to each of these little points, I have one function attached. So in the extreme case, you could say, take this R alpha such that it's 1 here, 0, 0, 0 there. The first alpha function will be attached here, the next will be attached here, here, and here. So you can see it's always possible to do this. But of course, the singular value decomposition does this in a cleverer way than I just explained. It does not just put 1 here, and then F1 here, then 1 here, F1 here, F2 here, and so on. But it chooses those functions in such a way that these terms here drop off as quickly as possible, and if it ever can, will make the largest values as small as possible. So if there is some structure in there, then basically this will be reflected automatically by lambda 3 and lambda 4 being much smaller, say, than lambda 1 and lambda 2.
This means if I go to this, the linear shape function would then drop off as quick as possible because it would be 1, 0, 0, 0.
A linear function drops off extremely quickly, yeah, absolutely. The linear functions require nothing.
It's some sort of typical finite sum.
Yeah, exactly. Linear is very easy to do. Linear drops off immediately. Okay, but as I said, we're going to repeat this. So what I'm going to do now is I'm going to basically, after rewriting this function like that, I'm going to look at the next term and do the same thing again. So now I have this kind of coarse grid where I have this function R0 that is encoded into my first 2 qubits, and I have the rest of it. Okay, and now I do the same step again. I take all the rest of it and again chop off 2 qubits for each. So I basically rewrite the grid in such a way that for each of these coarse grids, I define another grid. This is the green grid here, with another 4 points. So the red point here would also be a green point. Here, 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 I have the next finite grid. Okay, and again, I have the next finite grid and define that everywhere. And so I just repeat the same thing again. I basically, this was the first sum we've developed. Now I do a second sum. And again, chop off an R alpha beta now, where I have one index alpha, that is the same as this alpha here, tells me to which on the coarsest grid this is attached to. Then I have a beta here, that basically tells me which of these points is attached to, and then this little F alpha beta, that gives basically all the rest of it. That's again the finite. Okay. And now, of course, we can ask, how many terms can we now have in this sum? Well, you have alpha beta each can be 4, so we have 4 times 4, we can have 16 terms. Okay? And now, of course, again, the SVD will automatically choose these 16 terms in such a way that the diagonal term drops off as quickly as possible and gives us the minimum number of terms that we need. Whereas a kind of stupid approach that I would do is I simply say, well, pick all of these 16 points with 1, 0, 0, 0, 0, and just that would be the stupid approach. So let the computer do. Okay, now you can see the scheme already. What you do is now you basically repeat this approach. You always chop off 2 qubits and you look at how many terms do you need. And what you can also see is that, of course, in each step, the number of possible terms that you can have goes up exponentially. So if that number of terms really does go up exponentially, you will end up with exponentially many terms in the sum. So there would not be any advantage here. But now, of course, and I can kind of do this again, and I can do this again and again and again until I reach the end. And now, of course, initially, the number of terms will need to go up. But then, of course, towards the end, it will need to go back down again. So it will go up exponentially. And then when you get to final bits, it will need to go down again because I've got a finite size of a quantum register. So my number of correlations will need to go down again. And in principle, what you get is like a pyramid with a little kind of base at the bottom. And this is how this pyramid would look like. So here we have various different partitions. So that's basically where do I chop the grid. And here is the maximum number of terms in the sum I can get. So we started at 4, then we get to 16, then 4 to the 3, and so on. Here to 4 to the 5, and then back down again. And if you do the whole thing in 3 dimensions, we would not chop off 2 qubits, but we would chop off 3 qubits to basically fill octants with increasingly fine grids. So we start at 8, then 8 to the 2, 8 to the 3, and so on. Okay, and so in principle, we can need all of those terms. Now, because it is known, and I think I shouldn't say really it is known. I know there are some exceptions, and probably it's not always true. But in general, what happens is that all of these kind of fluid dynamics problems have some kind of strict structure in different length scales. So very large eddies don't interact directly with very short ones. And I recently read this kind of nice poem that the guy in 1929 wrote. How you go, the larger eddies feed on smaller eddies, and smaller eddies feed on even smaller ones, and so on and so on and so on until they get eaten up or something. It's kind of nice. I have it somewhere, and of course I would. Sorry. Until viscosity, exactly. So of course I wouldn't show you guys that, but when I talk to quantum guys, I kind of show how poetic. Fluid dynamics can be. It's always good fun. But I'm not going to show this here. So basically, because of that, what you would expect is that when you chop off length scales, you don't always saturate the amount of correlations that you have, because basically that would mean that the very largest eddies would need to directly interact with the smallest ones. If you had equal or kind of very strong interactions between all length scales, then that would mean that you saturate correlations at all length scales. But that is not the case, and we can quantify this now by looking at how many terms do we need in these sums. And what we see here is the number of terms that we need in order to get a high accuracy of our trial solution through these red lines here. So this is for various different times of the evolution of the two-dimensional jet evolving. So you see here that the number of terms that we need in this sum is small. It's exponentially small because this is a logarithmic scale here. So basically the maximum we could get is 4 to the 5. The maximum we do get is somewhere between 4 to the 2 and 4 to the 3. So this upper part of the pyramid here is completely empty. And this upper part of the pyramid looks small, but it is in fact large because of the scalarity. And so if we now chop in our algorithms, if we chop the pyramid off like this, basically fixing or limiting the number of terms that we can have in the sum, we chop off an exponentially large part, which it turns out from our kind of decomposition here is not needed anyway, because this never gets filled in these examples. And by the way, these solutions were obtained by just standard direct numerical simulations, so no approximations there. This is the kind of numerically exact solution. If, however, you do an under-resolved grid, this is, I think, the was suggested to us. We didn't come up with this ourselves. That's basically the kind of simplest and probably least well-justified approximation, that you should simply drop off the grid. Is there a question? Oh. Dimitris.
Yep. Sorry if you go back to the previous slide.
Yes.
So you said, yeah, this silly ways to, to just do like amplitude encoding, as many grid points as a bit string, and then you have all the, all the possible quantum coefficients to map your grid. You don't want to do that.
That's not what I said. That's exactly what we do. The silly way.
That's the quantum. That's the whole quantum encoding, quantum speed up. But then I'm just trying to see this. That now the tensor network, the MPS goes and sits on top, and then you save in parameters because you get a computer to keep the most important ones out of all these guys, basically. Because if you just do it by hand, you have a multitude of numbers, and it's hard.
I haven't said that yet. No. All I'm showing you now is that it is enough to have a low bond dimension matrix product description of your tri-wave functions, of your tri-states. We haven't created anything yet. We have taken a numerically exact solution, analyzed this in terms of the correlations that are needed, and we find that it doesn't saturate the correlations because we basically can chop off the top of the pyramid without making any mistakes. I haven't actually created them in a trial network or anything like that yet.
So my confusion comes that if there is a classical problem, then you map into this quantum state, the big quantum state, before we do any compression by MPS or whatever. Okay, let's assume that that's what you're doing at some point. Right, you map this QCFD problem to a quantum ansatz. That quantum ansatz can be hard to implement because at certain points you have entanglement, and then it's hard to simulate actually. In quantum body dynamics, we have a feeling where the compression, whatever compression we use, will work and well, it will not. For example, in the phase transition point, it fails, entanglement grows, blah blah blah.
Okay, so let me say the following then. So if you don't know anything better, then just implement a quantum network that realizes a matrix product state, and you know that you can do this in chi-squared gates, which is better than what you could do in classical computers where you need chi to the 4, so you get a quadratic speedup in generating those states. You can stick with matrix product states. If you go beyond that, I agree, it's less certain as to what you will get, but potentially you get a much bigger speed up. That's something we still need to look at. We don't know that yet.
But there is no intuition from the physics of the QCFD model, like the different phases.
There is. No, there is. I'm going to show you that in a minute. There is intuition. I mean, the first intuition here is that you never saturate entanglement. That's the first intuition, okay? In that measure. But I'll come to a little bit more in a minute, okay? What that means. So basically here we see that we always kind of get away with a very limited amount of entanglement, and hence, of course, if we can chop off that top of the pyramid at some fixed value, then what we would get is always a number of terms in our sum that grows only polynomially. So we've basically changed an exponential scaling to one that goes linearly with the number of grid points. Okay, so that means that's a huge kind of change in the scaling with the size of your system. And that's precisely what we want to make use of. Of course, it comes with, it doesn't really go one-to-one from a scaling of exponential of n to n. It also has a scaling with chi in there. So where we make that cutoff will actually determine how the algorithm scale, but that goes polynomially. And the question is, how does it go polynomially? And in classical, the best we know when we just try to simulate this classically, the best we know is that this goes like chi to the power of 4. And quantum mechanically, we know this will go like chi to the power of 2. So chi typically will have values on the order of a couple of hundred to a couple of thousand. And if you thus have an improvement of a chi squared on the quantum computer, that improvement is a factor of 10,000 to 10 million or something like that. So this could in principle be significant. And one of the advantages here in this case, I would say, is that this is a kind of known advantage that you get. If you compare one-to-one the classical implementation of this code with the quantum one, we know we get this speed up. Okay, and that I think is a nice thing that we know that kind of speed up exists. Okay, now of course here I just chopped off. You want to basically know also how much you've chopped off. So you can see that here this is again a logarithmic scale going from 1 to 10 to the minus 16. Here this kind of dashed line is where we did the chop off before, and you can see that there are some regions here where you get things on the order of 10 to the minus 12, minus 11, 10 to the minus 8. Those are the things we chop off. They basically contribute less than 1% to the overall solution, and hence we can easily chop those off. Now a bit more on the structure that Dimitris was just mentioning before. So if we look at different flows, and we've taken two examples, one in 2D, a kind of jet that forms, I'm going to show this a bit later, I'm not going to show this, I guess, a jet that forms in 2 spatial dimensions, and in the other case, in 3 spatial dimensions, a Taylor-Green vortex that decays. What we see is that this kind of so-called entanglement entropy, so this is now takes this Schmidt numbers that we had before into one single number that basically quantifies how much entanglement is there between 2 bipartitions of a system. And instead of having a whole set of numbers, we take the entropy of that set of numbers, and that quantifies how much entanglement is there. So it's a bit kind of counterintuitive, because in this case, we have entanglement of a subsystem of 2 subsystems being quantified through the entropy between those 2 systems, where you usually think entropy means disorder, but it turns out that when you in a quantum system get rid of one part of the subsystem, the bigger the disorder you leave behind, the bigger the original entanglement was. Okay, so this is a bit maybe counterintuitive. So if we look at what happens in 2D and what happens in 3D as a function of time, we see here that in 2 spatial dimensions, the amount of entanglement between different length scales moves from the blue curves that we see here at small times to the red curves that we see at long times. So this means that initially, much of the entanglement, much of the correlations are at the very kind of smallest length scales. And as time goes on, these correlations move to larger and larger length scales. And that's, of course, precisely consistent with the kind of usual notion that in 2 spatial dimensions, you have an inverse energy cascade, and hence energy should be transported to this way, basically from these kind of blue curves to the green curves. And in the 3D case, we have exactly the opposite happening. There it's maybe not as clear to see, but basically if we start right here at small times, we have got in the different directions, because there are 2, U1 and U2, there we have the opposite happening, namely that the energy cascade should go to finer and finer length scales, so the entanglement shows up at smaller and smaller length scales in the 3D case. And so to some extent, therefore, from this kind of entanglement spectrum and from this entanglement between the different bipartitions of the quantum states, we can say something about what is the correlations at different length scales of the flow. And of course, this kind of entanglement spectra have been analyzed in the quantum version of this type of physics a lot. And it turns out that they can give you a lot of very interesting information there. They can indicate phase transitions, as Dimitris was mentioning before. They can indicate some kind of interesting physics happens. And of course, one of the questions that we haven't fully answered yet is that something similar here? Can we actually look at these entanglement spectrum in quotes and learn something about the nature of the correlations in some flows? And can we analyze these types of correlations through these entanglement spectra? Entanglement always on the quotes. Yeah, you had a question?
Yeah. So basically, if it is so, then this approach would be beneficial in that way that we do not always need to run a DNS before we come up with the MPS. But if it turns out to be not, we of course need to invest time in order to learn our MPS.
No. So basically you don't, because you never need to run a DNS before, because what this approach, what the MPS approach immediately tells you is whether it has converged or not. So as soon as you run every step in the matrix product state version, you chop off, you know how much you chopped off. So, basically, So you chop off, you know how much you chopped off, you can estimate what is the error that arises from me chopping off certain parts. And if that becomes too large, you should have done the TNS.
I know it without this solution.
No, you know it as you work out the solution. So you basically you run the time step. Okay, you start with some initial state as a DNS. As a matrix product state. It's usually something simple. Then you evolve it in time. Every time step that you do will always increase the bond dimension. Okay, and initially, of course, it will increase that bond dimension within the limits that you allow it. At some point, then it will reach the limit where you say, "Oh, oops! Now I can't keep track of that anymore. I need to start chopping it off." So you set the boundary and say, if my bond dimension gets bigger than 500 or whatever, I chop off. And then you track how big are the numbers that you chop off, and the value of those numbers allows you to find out how big is the error in your numerical simulation that you do.
But to come up with that MPS,
yeah,
I do not need any data.
No, you just
okay. Then this is still gray for me, but
so
figure that out.
No. The initial condition, you need some kind of initial guess or some initial flow, but then the MPS that comes out of what I showed before, this optimization. So the V star that I had before comes out of the previous V, and that the input or the data you need is the previous V and your equation of motion that tells you how to step forward in time. You don't need anything else. Okay, and I think, when do we have? 1 o'clock is.
Well, at 1 o'clock, but I'm looking outside.
Oh,
but there's no one. There's no one.
That's not good. There should be somebody there. Maybe it's check. Yeah. So there's stuff there for us too. Okay, good. So that's what I was saying before already. If we now look at generating these matrix product states on a classical computer, we know that the classical complexity of doing so goes up like this bond dimension to the power of 4. But there are quantum networks, and so those are the quantum networks that you can use if you want to stick to matrix product states. You have in principle this format shown here that have a complexity that goes up like chi to the power of 2. In addition, all of the other terms that we looked at, namely the terms that would generate these differential operators, they all go at least polynomially, at most polynomially with the number of qubits. So they go like a polylog of the size of your system. And hence, the scaling here, this complexity chi to the square, is the most severe scaling on any kind of quantum algorithm that you could get. That rest of it is tiny and you can ignore essentially. So this would be the bottleneck. And that is now for the type of variational networks where you restrict yourself to matrix product states. Of course, you don't have to do this. You could just, if you wanted to, use here arbitrary networks like the one I showed before. In that case, you usually get something that whose entanglement grows a lot quicker with far less deep circuits. But of course, it's very hard to then understand what is the structure of these variational states that you generate, and would you get barren plateaus and all of these kinds of things. But certainly, it is worthwhile investigating whether you should look at other networks and other quantum networks to improve the accuracy of your trial functions and how to do so.
You don't get barren plateaus.
With the matrix product states, usually not. But again, there are nowadays a lot of methods that avoid barren plateaus. That is classical shadows that one can look at and so on. And so there are certainly other strategies that one could use. And that's something that what we need to look at as well, how to combine all of these different ways of avoiding barren plateaus and local minima and so on. Okay, so that's basically what I just said now is one thing I wanted to also mention briefly, and then I think I go for a lunch break. Because one additional thing that one could now ask or can now ask is, of course, when we actually step these types of functions forward in time, the quantum network that we get should or will usually become bigger and bigger and bigger. And as you've seen on some of the previous slides, we sometimes need terms like V star minus V, which V star and V will not be so very different. So there is the question then, can we compress these types of networks such that they never really grow in size? And we've developed a kind of systematic approach that recombines circuits, and this is published in here, which works entirely in quantum computers and basically allows you to take a quantum network, say that provides you the variational solution for the velocity field at time t. And then there is an additional network that steps that time, that velocity field forward to time t plus delta t. And then take this network and compress it so that it doesn't grow in size. And that's an approach that is called incremental structural learning. And that basically enables you to keep networks small. And we did that approach for some of the previous types of computations that we were running. And there basically this made a huge difference, the kind of networks that we got by a factor of 10 or so shorter than the unrecombined ones. And some of the PhD students I had then submitted this to IBM, and they won the IBM prize for this and that with this incremental structural learning approach. So basically what this means is that there are lots of tricks that one can play in addition to what I just showed today to shorten these variational networks and make sure that they can be created, or these variational trial states can be created with the smallest number of quantum gates possible. And all of that will provide advantages on top of this quadratic speedup that we know exists if we just take the kind of simplest approach implementing matrix product states. Okay, I do have a bit more, but I think time is up, and I'm happy to answer questions. And this thing is on the Teams website, so you can just go there and download all the kind of another 30 slides with more explanations for you to look through. One thing I did there also is I tried to explain why it is important to have ansatz that are physically motivated. Because if you could argue, well, let's just take an ansatz that can do anything. And if you take an ansatz that can do anything, you're guaranteed to get barren plateaus. So you want to put some brain into how to choose your ansatz. All right. Is there any questions? Yes, Tom?
I was kind of lost.
Thanks.
What's the quantum state representing? So if you have 0, 0, 0, 0, 0,
yeah.
Is it a single point in space, or is it?
That's a single point in space.
So then, how do you get the star out of at some point out of?
That's a super. So 0, 0, 0 means the probability amplitude at the point 0, which is 1, 0, 0, 0, which is one grid point. The one that's labeled 0 with a vector on top is 1, all the others are 0. Now, if you start to produce superpositions between different computational basis states, then you get non-zero values at different parts of the grid. And so you basically just produce your functions by taking your function values and writing them as probability amplitudes.
Okay.
So it's called amplitude encoding. If you go to the machine learning quantum version that they try to do, they call this amplitude encoding. Yes.
Quick question.
Sure.
So if we stick to that level of description, sorry for me, I'm just trying to understand. So if we stick to the amplitude encoding, we do our control swap or our control, ancilla, old school overlap, Mach-Zehnder stuff.
Yes.
We solve the CFD problem, and at what level, like what does the MPS exactly bring into the table that is not in the first level? Okay,
so what it brings is, in order to do what you just said, you need to generate the state, the fluid, the kind of velocity field in some way.
Right.
And when you generate this, you want to know that the network you need is not exponentially deep, to give you a good representation.
But I have the amplitude encoding, and that's exponentially big, right?
Yeah, but you need to get the amplitudes in somehow. You know, if you just will go one by one,
Load, you're trying to solve the bottleneck of the machine learning problem to load the data.
yes,
To load the data, okay, yes, we have quantum exponential speedups, but how do you really load the data? How you get the machine to? Because if we want to go to finer and finer grids and look for all these exotic turbulent whatever effects, it's gonna blow up. That's why you're gonna need. Okay.
right. And that basically that's what I solve here. So getting the data in, getting the amplitudes in, is doable via a small network that only grows like chi-squared. And this does not require exponential, because that's exactly the bottleneck that you mentioned in any kind of quantum machine learning approach. So you don't have that here, because your data, I mean, first of all, it's not real data. It's basically you start with an initial state, and then you just want to make sure you can represent this. But the data has some structure, and you utilize this structure here. And the structure comes from this kind of energy cascades, or these kind of different interactions, length scales that you have in fluid flows.
I see.
That's what makes this work. Otherwise, you know, if you were completely structureless data, you could end up with variational networks that never converge because they need to be exponentially deep.
Right.
But of course, you know, to some extent, you have the same issue in classical physics. If you take an arbitrary Boolean function, that requires exponentially many NAND gates to realize. But, you know, for some lucky reason, this is never really needed. And here it seems similar, that we don't need this. We get away with small networks in order to generate these fluid flows.
But so, Dieter, sorry, but this is due to the fact that you say that, okay, you can make an ansatz that is an MPS.
Yes.
And then you see that, okay, you can continue with that. So this is somehow the idea. Is this correct?
Right. Yeah, that's the idea. Yeah, so that's the idea. And the physical reason for that was, as I tried to explain before, that interactions in these fluids happen between different length scales and not across all the length scales. Yeah. So we don't have an area law like you have in quantum physics. I guess there might be one, but just like in spin physics, if you have only local interactions between the spins, you get an area law that tells you how much entanglement you can have. Here you have interactions that are local in the length scales rather than in distance. And so you would expect something similar to happen, but I don't think it's rigorous here. And of course, the nice thing is that length scales are always one-dimensional. So, you know, in quantum systems, you have 1D, 2D, 3D. Local interactions mean something very different and lead to totally different behavior of the entanglement. Length scale is always just one-dimensional. So you always have a boundary of length scales. If you draw different length scales, that doesn't grow with the range of length scales you cover. So you would hope that, you know, entanglement doesn't grow too fast. And yes.
Yes. So basically, as I understood, we have now two concepts. We have this variational approach and the MPS approach.
Yeah.
Is the MPS approach somehow also embedded into that variational approach by executing the ansatz and the QMPU and feeding in the MPS?
Yes, you're absolutely right. So basically, we can now, of course, decide how to proceed. And we know we can generate these MPSs on a classical computer with a chi⁴ task. Then we can, of course, do this optimization through standard density matrix renormalization group techniques, time-dependent block decimation or whatever, all the kind of tools that you have in quantum physics, and you can run a purely classical version of this. And that, of course, we were surprised that on a laptop we can compete when we do that with the kind of some of the standard methods that I used for some of these differential equation solvers. This works pretty well. I mean, given that we didn't put years and years into it, we were competitive in essence after a couple of months with that. So that I think is great. But mainly what that does is it does tell us, it can allow us to show the scaling of the algorithms if we were to put them onto a quantum computer. So we can precisely from those simulations, we can precisely tell how long would this run on a quantum computer. And hence we could tell what is the hardware requirements in order for you to see a quantum advantage. And that's what we promised in this project. Okay, we didn't promise to get a quantum advantage. We promised to be able to say, if this hardware exists, you run this, you get an advantage. Okay, and so for that, we need a purely classical simulation with these matrix product sets.
Regarding quantum speed, I've understood the variational quantum approach seems to be more beneficial since the MPS is only leading to the most basic gate sequence, which is leading to that outcome. So when we use that variational quantum approach now, we end up with the probability effects of the quantum machine somehow. That's just then also reflected back in the results. This is, of course, not gathered in the MPS world and also not in classical MPS world.
No, but you can of course, okay, you can work this out. We haven't done this yet, but essentially what you're saying is what you need from the MPS simulation gives you the full quantum state. It gives you the kind of wave function in essence. So of course you can then easily work out what is the expected value, but you can also work out what is the variance. And if you know the expected value and the variance, you can estimate how many times you need to measure, how many runs you need to do. So we can have this. And we have done this in our first paper on this nonlinear Schrödinger equation. We have given exact estimates of the errors and how they scale with the number of shots you need to take. And you get the typical behavior. It goes like 1 over the square root of the number of shots, but the pre-factors were small. And so what we found there is that the number of shots is reasonable. It's kind of maybe 100,000 or so to get good estimates. But of course, this is going to be a challenge. There's no doubts about that.
Okay, and there, of course, the variational quantum ansatz is the main construction side in order to get the accuracy, because it needs to be either it's too complex and we end up with the Barren plateau problem, or we have a physical motivated one. Yeah. So if we do not have a good ansatz, probably coming from the MPS, I don't know, might be
right. That's true.
Okay.
Again, it's what I said at the very beginning. It does not solve your classical optimization issues. This is something that one still needs. So the kind of expertise in knowing how to optimize classically remains. It just gives you a much more efficient way to compute the quantities that go into the optimization in some ways. And that's also why I guess we are here together, because you know one thing, we know the other, I guess. and it's not I couldn't do it myself, and I would not, but because you need to know exactly what is the physics behind all of this to really do these optimizations and variations properly. Yes.
Quick question, so for example, in your MPS simulation, for example, first you use 10 qubits. So you get the result of your final fluid field.
Yes.
And in the second experiment, you use 20 qubits.
Yeah.
So can I expect the first 7 qubits are predicting the same result? Because first you have a short coarse grain model, and then you have a more finite.
No, you can't. So basically, you cannot. But what you can do, of course, is you can run your computation with first 10 qubits, say, and then do what we call a kind of prolongation step where you add a qubit. And you add that qubit in such a way that it gives you a linear interpolation of the coarse grained one, and then you run optimization again to get better results. So you can build up your finer and finer solution by adding qubits and prolongating the solution to that, and then optimizing again. But the solution, the coarse grained solution you get, is not going to be the coarse grained solution of the fine solution. So that will not be the case. So you will have errors in there.
Yeah, I mean, now when we are adding more and more qubits, can we reproduce the previous result, which with not so much qubits? Because
yeah, sure. Yeah, absolutely. Now, this is what I mentioned at the very beginning. So basically here, what I said was that we do not need to measure here. In order to get the cost function, you only need to measure the ancillary qubit. We don't need to measure these. But one thing you can do is you can basically put a couple more gates, single qubit gates here, and measure them, and that will automatically coarse grain your solution. So you can do two things. You can coarse grain your solution as much as you like. And basically what that coarse graining will do automatically is average over all the finer grain parts of the solution, average out the fine details, and give you a coarse grain image of what you have. Or you can zoom into a part and then kind of just measure the flow field in a little part of the system. This is something which is not published, and I don't think we will publish it anytime soon, but it's possible.
So this QMPU is with the coarse grain version of the coarse function. Right?
Now the QMPU evaluates these operators here applied to the functions. So this basically will be the Laplace operator or the divergence or something like that. That so will be encoded.
This coarse function, we don't know get to the old.
So here you know
the previous slide. So from this part, I call it coarse function, the one above. So where it's not like entirely trivial to how to get to one.
This one here. Oh no, this is I think at least this should be relatively straightforward, because you here basically would say for this case you have V star would be one of your F's. Okay, then the operator would be the Nabla operator would be this operator OJ here, and so on. So basically you just, I've just written it in this general form because all of these terms that you have here are of this form. So V dot Nabla V, you could write it like that.
But my question is why do we still need to search for the bunch of problems as well?
Oh, because you don't know the V star.
Oh, okay.
So you then basically you know the V in this case, but you don't know the V star. Mm-hmm. So you would basically optimize your parameters lambda to get the right V star. Okay. So how would you do this? I mean, the V star should be the time evolved thing. So you would basically take the V and apply a couple more gates to it to get from the V to the V star. Mm-hmm. And then those extra gates, that would be what you need to optimize. Okay. Each step.
Yes, but so then continuing on that train of thought, so your V star should be quite close to your V, right? So yes. Is it not true that why would you need a global optimizer? Is it non-linearity?
Yeah, this is a good question. That's something that will probably depend on here. If we do a time evolution, you might get away without that. But of course, very often you don't want a time evolution, want the stationary state. We start from some starting estimator. So it depends on what you do. But as long as you do small time steps, you might be right. You might get away with just small network. But that's also the reason why I said, we then would propose to do this incremental structural learning, where you basically take the previous V and the new V star and combine that into a smaller network, as small as possible. And then you have a new network that creates the V star automatically. So yeah, but this is what something that one can do now. I mean, I should also add that, of course, it's only now becoming really possible to run this on actual quantum computers. When we first started doing all of this, the biggest computer we had was 5 qubits, and the C0 gates were so bad that after 2 C0 gates, the whole thing was more like a random number generator. And so we couldn't get too much done. But nowadays it gets better, and so one can start to actually think about doing this again on the actual machines. And that's what you're building. So
yeah. But we're not like that.
They are much better now than they used to be. So it basically does become better at a good pace. And to me, surprising. I mean, if you look at the latest ones, they are not so far from the error threshold anymore. And of course, once they reach error threshold and they can scale up, then you basically can do error-free quantum computing. And they are probably a couple of tenths of a % away from this error threshold. So it's not so bad anymore. Are there any other questions? Yes, please.
What's going to happen if the flow is turbulent in the time movement?
Well, good question. I mean, that's precisely one of these questions that I said before. We know from quantum mechanics that this entanglement spectrum shows you a phase transition. And the same holds here. I mean, one of the first questions I asked the PhD student, who is now, of course, doing something different, was look at the entanglement spectrum in a turbulent. DNS, I mean, from direct numerical simulation, turbulent flow, non-turbulent flow, put the two on top, do you see a qualitative difference? Does the entanglement spectrum show you a transition from a turbulent to a laminar flow or vice versa? And can we from that find out what the nature of this is? Is this a sudden transition? Is it smooth? Is it crossover? Or what is it? I think this is still an interesting question. Anybody who wants to have a go at it, I think this is a good question, I believe. Yes?
So I mean, near the phase transition, maybe instead of using MPS, we can use like narrow.
Yeah, you can do that. Perfect, do that. But bring a lot of time for doing the coding. This is not easy. But yes, sure. So of course, when we submitted this paper, first question by the referee, use other networks. And we said yes, but then it would take another year or so, and then we sent them, said this is beyond the scope of this paper. But this is something that I think has a lot of potential, but it is really, really tricky. Okay, it's not straightforward to do. And so on the other hand, I said what I just said is you have this hierarchy of scales in flows. And tensor and matrix product states are ideally suited for it. So if you take this, or as long as you can take this seriously, that interactions happen strictly between neighboring length scales, there is probably not a very good reason to go to something different. I guess people are waiting out there already, and we are hungry, I guess. So,
Do we have to leave the room?
yes, and we do have another room in the afternoon, so we will be in a different seminar room just across the corridor here. It's not very far away, but this one was only in the mornings. Okay, we can always talk later. But I'm going to switch off now for lunch, and we'll be back online in about an hour from now.
So we do start at 2:30, Peter, again?
Yes, yeah, 2:30 should be fine. Yes.
Okay, good.
All right.
Yeah.
Right.